So in the last movie, I talked about the silver ions added to the various halides and then what happened when you added various forms of ammonia to those precipitates. Now we're going to focus in on lead. Now we're going to do a lot more with lead for two reasons. The first is that many schools don't mess around with lead because it's really tough to dispose of. The second thing is that it's actually a bit more interesting. But anyway, let's take some lead and we're going to add various ions to it. The lead is in the form of lead nitrate. Anytime you see a nitrate, you know it's going to be water soluble. So lead nitrate, no problem. Nitrate ions floating around as spectator ions, lead 2+ ions floating around. We're going to try first of all adding some magnesium chloride to that. So magnesium chloride, we've got chloride ions in there. And what we saw is cloudy solution. Okay, and that's the result of lead ions getting together with two chloride ions to make some lead chloride solid. Now it's cloudy because that's a precipitate, but it's not a huge amount of precipitate for reasons that we'll discuss in just a second. Anyway, then we took a second sample of lead nitrate and we added some calcium bromide to it, and that's a precipitate, a really thick white precipitate that's formed again, lead ions catching on to the bromides to make the lead bromide in the solid. And now finally, in terms of the halides, the one you absolutely need to be able to recognize, take a solution that's got lead 2+ ions in it, add to it a solution that has iodide ions, and you get this vivid yellow precipitate there that is of lead iodide. And just to emphasize the point, I put a little yellow box around the lead iodide to really emphasize you see a nice bright yellow precipitate, and there's a chance that you had lead ions and iodide ions. Lay a bet that it was lead iodide. Now, in the same way that I mentioned some equilibrium constants for the silver, let's think of some equilibrium constants here for the lead. Okay, you take lead ions, you have chloride ions, put them together, you make a precipitate of lead chloride. That lead chloride precipitate, it can be in equilibrium with lead ions and chloride ions. It's a pretty small equilibrium constant, but notice it's much, much bigger than the silver equilibrium constants that we saw. Okay, so even though most of the lead ions and the chloride ions are going to be back in the form of lead chloride, there'll be enough lead ions and chloride ions floating around that aren't in the form of lead chloride that you don't see that full thick precipitate like you do for the bromide. It's just enough precipitate to make it cloudy. Moving to the bromide, however, lead bromide splitting apart to lead ions and two bromide ions. Now you can see you've got a smaller equilibrium constant, not hugely smaller, but obviously sufficiently smaller that you go from the cloudiness for the chloride to the thick white precipitate for the bromide. And then finally, of course, lead iodide, even smaller equilibrium constant. By the way, what this essentially means, the way that those equilibrium constants for the solid dissociating to the ions, solid dissociating the ions, solid dissociating to the ions. The smaller equilibrium constants means that the lead chloride is more soluble than the lead bromide. The lead bromide is more soluble than the lead iodide. So for lead ions, the solubility decreases as you go down the halides. Okay, just something that you might need to know at some point or other, probably not for the A-levels. Anyway, so there was the lead halides, very important you're aware of those. Take lead, mix it with sulfate, we get a white precipitate. And that white precipitate is, of course, lead ions plus sulfate ions, making that lead sulfate precipitate there. Take lead with carbonate, we see a white precipitate. I'm not going to give you a picture of that particular white precipitate because let's face it, one white precipitate is often very much like any other white precipitate. Take lead ions and add the hydroxide to it and you get another white precipitate. Now again, I've sort of got this so you're halfway through the process just to emphasize a little bit, but lead plus hydroxide ions gives you a white precipitate of lead hydroxide. But then if you keep adding hydroxide ions, so we keep adding sodium hydroxide to this, it dissolves up that precipitate. So this is after we've added more sodium hydroxide, added rather concentrated sodium hydroxide to it, so I didn't have to add a huge amount of extra volume. And the reason for that is that the extra hydroxides will react up with that lead hydroxide, the solid lead hydroxide precipitate, to make this tetrahydroxide lead dianion here that is soluble. Now that is illustrating a very important property of lead oxides and lead hydroxides, and that is that they are amphoteric. They can act both as acids and bases. Here it is acting as an acid, reacting up with further hydroxides. Okay, so lead ions are amphoteric, and in a future movie we'll talk about some other ions that are amphoteric. There's a list of 4 ions really that you need to be familiar with for the GCSE, for the A-level, in which the ions are amphoteric. So anyway, there's the lead associated with the experiments that you did.